Hi, welcome back. What was the previous video about? Laplace transform of unit step function, right? In this video, we'll go through Laplace transform of Dirac delta function. So happy learning, and don't forget to like, share, subscribe the channel and press the bell icon.
Today we'll discuss the topic Dirac delta function and its Laplace transform. Dirac delta function is an idealized model of a very large force or input acting over a short period of time. Look at this. This function del of t minus a is equal to infinity and is acting at a single point t equal to a. That is, at this point t equal to a, this function tends to infinity. You can take the point anywhere, and at that point this function tends to infinity. Such a function is known as Dirac delta function or unit impulse function. Why unit impulse function? The unit here indicates unit area. That is, the area of a Dirac delta function is always equal to unity. And you can find its applications in mechanics, signal processing, electronics, etc. And these functions can be considered as pulses. So it can be defined as a pulse with infinite height and zero width and having unit area. And this function is considered as the limiting case of other functions. So I'll explain you that. Consider a function del k of t minus a, which is equal to 1 by k when a less than or equal to t less than or equal to a plus k and 0 otherwise. Now we can represent this function like this. That is, this function will be equal to 1 by k when a less than or equal to t less than or equal to a plus k and 0 otherwise. The width of this function will be equal to k, right? That is, a plus k minus a will be equal to k. So this width will be equal to k. And this height will be equal to the function value, that is 1 by k. So the area of this function will be equal to 1 by k into k, which is equal to 1. So this function is of unit area. Now what happens if k tends to infinity? If k tends to infinity, this width reduces and this height increases indefinitely in such a manner that the area of this function always remains equal to unity. That is, when this k becomes equal to 0, these 2 points merge to a single point a and this function value tends to infinity. So such a function is known as Dirac delta function and it is the limiting case of this function, that is del k of t minus a. That is, when k becomes equal to 0, these 2 points merge to a single point and this function del k of t minus a will be equal to del of t minus a, and that is the Dirac delta function. Therefore, del of t minus a is equal to infinity when t equal to a and 0 when t not equal to a, such that integral minus infinity to infinity del of t minus a dt is always equal to 1. That is, area under the curve is always equal to 1. So when these 2 points merge to a single point, this takes the form, see, at this point the function is equal to infinity. So we can write del of t minus a is equal to limit k tends to 0 del k of t minus a. That is, this function is the limiting case of del k of t minus a. Now at t equal to 0, del of t minus a becomes equal to del of t, and this del of t is equal to infinity at that point, that is t equal to 0, and it is 0 otherwise. That is, when t not equal to 0, the function will be 0, such that the area under the curve is always equal to 1. That is, integral minus infinity to infinity del of t dt is always equal to 1. Now look at this. The concept will be more clear to you. See here, the function del k of t is equal to 1 by 2k when 0 less than or equal to t less than or equal to 2k. Here the width is equal to 2k and the height is equal to 1 by 2k. Therefore, the area will be equal to 1 by 2k into 2k, which is equal to 1. Suppose the width reduces to half of this width, 2k. That is, the width becomes equal to k. Then the height increases to 1 by k in order to maintain the area equal to unity. Here also the area is equal to 1 by k into k, which is equal to 1. Now, when this width reduces to 0, that is, when this width becomes equal to 0, this height becomes equal to infinity, maintaining the area equal to 1. So, del of t is equal to limit k tends to 0, del k of t. Now, look at these box functions. The function del k of t is equal to 1 by 2k when minus k less than or equal to t less than or equal to k and 0 otherwise. Here, the area will be equal to 1 because the width is equal to 2k and the height is equal to 1 by 2k. Therefore, the area of this will be equal to 2k into 1 by 2k, which is equal to 1. Now, suppose this width reduces to half. Then this box function takes this form. That is, the function del k of t will be equal to 1 by k when minus k by 2 less than or equal to t less than or equal to k by 2. So that the area remains equal to 1. Here the area will be equal to k into 1 by k. K is the width and 1 by k is the height. So k into 1 by k, which is equal to 1. And when this width becomes equal to 0, this del k of t will be equal to del of t, which is equal to infinity, and that is known as the Dirac delta function. Now let's go through some of the properties of Dirac delta function. We already know the first one. That is, the delta function del of t minus a is 0 everywhere except at t equal to a. That is, at t equal to a, we have del of t minus a equal to infinity. And del of t is 0 everywhere except at t equal to 0, because at t equal to 0, we have del of t equal to infinity. Now the next property, integral 0 to infinity f of t del of t minus a dt equal to f of a. This f of t can be any function. And you can write this integral from minus infinity to infinity also. In general, you can write it as integral minus infinity to infinity f of t del of t minus a dt is equal to f of a. In textbooks and all, you can find this. See, here we have taken a point a which is greater than 0. So, we can write integral 0 to infinity f of t del of t minus a dt is equal to f of a. Similarly, integral 0 to infinity f of t del of t dt is equal to f of 0. Why? Because here a is 0. So, f of a will be f of 0. Now, I will show you some examples of integration. Given integral minus 4 to 4, 7 e raised to t cos t del of t dt. We have to solve this. Here the function is 7 e raised to t cos t, right? And a is equal to 0 here. So f of a will be f of 0. Now substitute 0 in the place of t. So 7 e raised to 0 cos 0, which is equal to 7, because e raised to 0 is 1 and cos 0 is 1. 7 into 1 is 7. Now next one, integral minus 4 to 3, 7 e raised to t cos t del of t minus 2 dt. Here a is 2, right? So f of 2. Therefore 7 e square cos 2. Now the next one is integral minus 4 to 1, 7 e raised to t cos t del of t minus 2 dt. Now here we have a equal to 2. Now look at the limits. Here in the interval, we don't have 2, right? So, since t equal to 2 doesn't lie in the interval of integration, we have this integral equal to 0. Let's see how we can find out the Laplace transform of Dirac delta function. We know that Laplace of f of t is equal to integral 0 to infinity e raised to minus st f of t dt. Therefore, Laplace of del of t minus a is equal to integral 0 to infinity e raised to minus st del of t minus a dt. Now we know that integral 0 to infinity f of t del of t minus a dt is equal to f of a. Now comparing these two, we will get f of t is equal to e raised to minus st. Therefore, f of a will be equal to e raised to minus as. Therefore, integral 0 to infinity e raised to minus st del of t minus a dt is equal to e raised to minus as. That is, Laplace of del of t minus a is equal to e raised to minus as. Now, Laplace of del of t is equal to integral 0 to infinity e raised to minus st del of t dt. But we know that integral 0 to infinity f of t del of t dt is equal to f of 0. Therefore, f of 0 will be equal to e raised to 0, which is equal to 1. Therefore, Laplace transform of Dirac delta function at t equal to 0 equal to 1 and Laplace transform of Dirac delta function at t equal to a is equal to e raised to minus as. Please do like and share the video and subscribe the channel. Thank you.